Quantum particles do not behave the way the world around you behaves. Even as you sit here, feeling still, steady, and certain of the space you occupy, the smallest pieces of reality are slipping through every rule you know. They blink in and out of states, smear across probabilities, and exist not in places, but in possibilities. At their scale, motion is not motion, position is not position, and the universe seems to whisper its truths in riddles rather than laws. If this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps these calm explorations continue, and your presence means more than you know. Now we drift into part 1, like turning a quiet page into the hidden world beneath all matter. Part 1. What happens when reality becomes a probability? If you could shrink yourself millions of times smaller than an atom, the solid world would begin to dissolve. Particles would no longer sit in one place or follow one path. Instead, they would spread out into clouds of possibility, mathematical waves describing where they could be rather than where they are. At this scale, certainty fades, replaced by a quiet landscape of probabilities that never stands still. It's the first sign that quantum particles do not obey the rules we expect. The first thing you would notice is how unfamiliar motion becomes. In the world you know, objects travel from point A to point B through a continuous path. But down here, paths lose meaning. A particle doesn't walk a single trail. It wanders across every possible trail at once, each path contributing a whisper of probability to its final outcome. What we see as a straight line or a gentle curve is, beneath the surface, the sum of many potential journeys collapsing into one. The universe, at this level, is not a story of objects moving, but of possibilities unfolding. If you paused in this quiet quantum space, though pause is too classical a word, you would find that even the idea of location begins to fall apart. Position is no longer a single point. It becomes a soft, spreading distribution, like mist drifting over a valley. The particle is not at a spot. It is most likely around one, and that likelihood changes constantly, shaped by unseen influences, nearby fields, past interactions, or the simple fact that a particle's nature is inherently uncertain until measured. What feels strange is that the particle is not hiding its true location. There simply is no definite location to reveal. This probability cloud is described by something called a wave function, a mathematical expression that tells us where the particle could be and how its possibilities evolve. It ripples gently through space, growing in regions where the particle is more likely to appear and fading in places where it is less so. This wave function is not a physical wave like water or sound. It is a wave of information, a quiet rhythm of potential outcomes. And as long as no one measures it, it flows undisturbed, spreading, overlapping, and forming patterns that can look almost like the surface of a calm pond after a stone falls in. If you continued drifting, you would see that particles can pass through each other's probability clouds with ease. They don't collide the way billiard balls do. Instead, their wave functions interfere, creating patterns of bright and dark zones, regions of high probability and regions where the probability vanishes entirely. This interplay is one of the most graceful movements in nature. Two electrons approaching one another do not bounce instantly. Their wave functions overlap, repel, reshape, and reorganize. The interaction is more like a dance than a collision. Yet this gentle world of probabilities is not as chaotic as it seems. Beneath the uncertainty lies a structure so consistent it has been tested in laboratories for nearly a century without ever failing. The laws governing probability waves are precise and predictable, even if the outcomes they describe are not. You can calculate how a wave function evolves with extraordinary accuracy, but you cannot say exactly where the particle will land until it does. It's a paradox that sits at the heart of quantum mechanics. Nature offers perfect rules to predict imperfect outcomes. Imagine following a single electron in this strange environment. At a macroscopic scale, electricity seems smooth and continuous, a steady flow. But here, each electron moves according to its wave function, exploring multiple possibilities at once. The electron doesn't slide along a wire like a marble in a tube. Instead, It occupies patterns of probability influenced by the geometry of the metal, the spacing of atoms, and the tiniest vibrations of the lattice. The flow of electricity becomes a story of quantum waves moving together, not particles marching in step. If you drift a little closer, you would notice something even stranger. As time passes without disturbance, the probability cloud broadens. The particle becomes less localized the longer it goes unobserved. It spreads out, exploring more of its potential space. This natural tendency to diffuse is not due to motion in the classical sense, but to the mathematical evolution of its wave function. The particle's identity is smeared across an expanding region until something interacts with it, an atom, a photon, or a measuring device, and gently collapses it back into a definite outcome. This collapse is not violent or sudden in the way the word suggests. It is more like a quiet condensation of possibilities, a narrowing of the particle's options into a single result. But the precise mechanism behind this transition remains one of the deepest questions in physics. What counts as a measurement? Does consciousness play a role? Or is collapse simply the moment when a quantum system becomes entangled with something large enough to register its state? No experiment has answered these questions fully, but all experiments agree on the behavior. Before observation, reality is a probability. If you could watch this collapse many times, you'd see patterns emerge. Drop a particle through a double slit 1,000 times, and each landing spot seems random. But over time, those random points form a structured interference pattern, a pattern that only makes sense if each particle explores both paths simultaneously as a wave. It's a reminder that randomness at the microscopic level creates order at the macroscopic scale, as though nature paints with both chaos and symmetry. Even more astonishing, if you tried to peek at which slit the particle actually passed through, the pattern disappears. The act of observing the path forces the wave function into a narrower state. The particle must choose one slit or the other, and the elegant interference structure collapses into a pair of simple stripes. In trying to watch the particle behave like a wave, you cause it to behave like a particle. In trying to determine its path, you destroy the very phenomenon you wish to understand. This sensitivity to observation has led some scientists to suggest that probability is not simply a lack of knowledge. It is the fundamental fabric of quantum reality. A particle's properties do not exist in the classical sense until something interacts with them. Until then, they are described only by statistical distributions. In this view, the universe is not a machine with hidden gears. It is a stage where possibilities exist freely until the moment they must resolve. As you linger in this fluctuating world, you begin to sense a quiet truth. Probabilities are not imperfections. They are the language of the microscopic universe. They allow particles to tunnel through barriers, to remain stable in atoms, and to form the foundations of chemistry, biology, and life. Probability is not a loophole, it is a guiding principle. In this chapter of our quiet journey, one question gently rises. If reality becomes a probability at the smallest scales, what happens when two particles share those probabilities together? Now we drift toward the next truth. Part 2. Why can a particle be in two places at once? In the classical world, a thing exists here or there, never both. But in quantum mechanics, particles exist in superpositions, occupying multiple potential states simultaneously. This is not metaphor, but measurement. Until observed, a particle behaves as though it lives in overlapping realities, each equally possible. It is one of the most gentle yet unsettling truths of physics, a reminder that nature allows options to exist before decisions. If you drift quietly down to the quantum scale, superposition doesn't feel like a trick or an illusion. It feels like the natural resting state of the universe. A particle doesn't choose a position, a path, or a state. It exists in all of them at once, its wave of probability stretching across every possible outcome. Only when something interacts with it, when it is asked a question by the universe, does it settle on a single answer. Until then, it is a whisper of many futures. To understand superposition, imagine a tiny electron approaching a fork in the road. In the classical world, The electron must choose left or right, but in the quantum world, it chooses both. It takes both paths simultaneously, each weighted with a specific probability. Its wave function, the mathematical description of everything it could do, splits into branches, overlapping and influencing one another. These branches don't exist in separate universes. They exist in a single, coherent state, woven into one elegant structure of possibility. If you could see this with your own eyes, it would be like watching a soft mist split and rejoin, drifting through multiple channels before gathering again downstream. At no point does the mist commit to only one branch. It fills the entire shape. A particle in superposition behaves much the same way, filling all of its allowed states like a gentle cloud, expanding to the limits of its mathematical container. But the moment you look closely, the mist collapses. The electron must pick one branch, and everything else vanishes. This sudden narrowing of options is what physicists call wave function collapse, though the name can sound more violent than the process truly is. Collapse is quiet. It is simply the transition from many simultaneous possibilities to one definite outcome, a narrowing of the universe's whisper into a single note. One of the most iconic demonstrations of superposition comes from the double-slit experiment, a test that has humbled physicists for more than a century. If you fire electrons one at a time through two narrow slits and let them land on a detector screen, you might expect two clusters, one behind each slit. But that's not what happens. Instead, the electrons form an interference pattern, a series of bright and dark stripes. These stripes are not caused by electrons hitting each other. They appear even when electrons travel alone. This pattern is the signature of waves interfering with themselves. It is the fingerprint of superposition. The electron goes through both slits. It interferes with the possibilities of its own journey. The pattern that emerges is not a map of where the electrons traveled, but a map of how their probabilities overlapped. Yet if you place a detector at the slits to observe which one the electron passes through, the interference pattern disappears. The electron no longer travels both paths. It chooses one. Observation forces the universe to answer a question it would otherwise leave softly unresolved. Some people interpret this as consciousness changing reality, but that is not what the equations require. In quantum physics, observation simply means interaction. Anything that interacts with a quantum system, a photon, an atom, a measuring device, counts as a measurement. The particle becomes entangled with its environment and can no longer maintain its delicate balance of possibilities. The wave function collapses, not because a mind looked at it, but because the universe imposed a constraint. If you could float beside a particle in superposition, it would feel like standing in a hall of mirrors where every reflection is equally real. Each reflection is a possible future. Each is weighted with a certain likelihood, and the particle exists in all of them until one reflection becomes the actualized world. But superposition is not limited to position. A particle can be in multiple energy levels at once, vibrating with several frequencies simultaneously. It can spin up and spin down at the same time, a state that forms the foundation of quantum computing. It can even occupy multiple interaction histories, absorbing a photon and not absorbing it, until something forces it to resolve. What makes this so astonishing is that superposition is not rare. It is not exotic. It is the default state of matter at small scales. An atom's electrons exist in superpositions of orbital shapes. Molecules vibrate in superpositions of different modes. Even the large-scale phenomena we experience, chemical bonds, photosynthesis, superconductivity, are built on layers of superposed states interacting and blending. The only reason we don't see superposition in everyday life is that macroscopic objects interact constantly with their environments. A chair, a stone, or a human body is entangled with trillions of particles at every moment. This entanglement destroys superposition almost instantly, a process known as decoherence. The microscopic world is allowed to remain uncertain. The macroscopic world is forced into certainty. It is as though the universe maintains two layers, one built on potential, the other on outcome. If you step back and consider this pattern, you can feel its quiet beauty. The universe permits many futures to exist. It holds them gently, offering space for exploration, for complexity, for subtlety. But when the time comes to choose, it chooses just one. This balance between openness and definiteness, between wave and particle, is what allows matter to behave both poetically and predictably. Superposition also holds a deeper philosophical weight. It suggests that the world is not a rigid sequence of events, but a fluid unfolding of possibilities. The future is not written, it is woven, and quantum particles weave it by holding every allowed path lightly until the moment they commit. These overlapping realities aren't fantasies. They are the scaffolding of existence, the silent background where the universe keeps its options open. If you continue drifting through this quantum landscape, watching particles shimmer between states, you may begin to sense the question that scientists still struggle with. Why does superposition end? What exactly triggers collapse? And could superposition exist at a large scales if decoherence were somehow prevented? Experiments with superconducting circuits and massive molecules suggest that the boundary between possible and actual is not as sharp as we once believed. And as we drift deeper into this quiet mystery, another question begins to rise. If particles can occupy multiple states at once, how do those states influence each other? How does the universe keep track of the hidden correlations between possibilities? Now we turn the page and move toward the next truth. Part 3. How can observation change reality? In everyday life, looking at something doesn't alter it. But at the quantum level, the very act of observing a particle collapses its wave of possibilities into a single outcome. The observer effect is not mystical. It is mathematical. Measurement forces nature to choose, turning uncertainty into one definite state. It suggests that at the smallest scales, reality is not simply there, it is interacting with those who look. If you drifted into this microscopic realm, quiet and unhurried, you would discover that observation has a very different meaning than the one we use in daily life. It does not require eyes. It does not require awareness. It does not require a conscious mind holding intention. In quantum mechanics, observation simply means interaction. A photon bouncing off an electron is a measurement. An atom absorbing energy is a measurement. Even the smallest disturbance, any exchange of information, forces the quantum world to settle into a definite configuration. Until that moment, the system remains a cloud of overlapping possibilities. Each possibility is not imaginary. It is encoded in the wave function, the mathematical shape of what the particle could become. This wave function evolves smoothly, predictably, following Schrödinger's equation like a calm river following its banks. But the moment an interaction takes place, that river ends. The wave function collapses and only a single branch of its many paths becomes real. The shift is abrupt, yet silent. You do not hear it, you do not see it. But mathematically, it is one of the sharpest transitions nature performs, the transition from probability to presence. To see this clearly, imagine a lone electron drifting through space. Left unobserved, it moves as a wave. Its position spreads, its momentum diffuses, it occupies a region, not a point. But let a single photon strike it, and the wave collapses instantly at the site of interaction. The electron is no longer a cloud, it is a single point again, an outcome crystallized from countless possibilities. This is the heart of the observer effect. Interaction forces the universe to answer a question it would otherwise leave open. If you place a detector near a double slit, you ask, which path did the particle take? Before the detector, the particle's wave function includes both paths. After the detector interacts with it, only one path remains, the interference. Pattern disappears, not because the particle stopped behaving like a wave, but because you forced it to reveal one of its identities. This idea feels unsettling because it suggests something profound. The world does not come pre-packaged with definite properties. Instead, properties arise through interaction. You might imagine this as a quiet dialogue between the particle and its environment. The environment asks, "Where are you?" The particle replies by collapsing into a location. The environment asks, how fast are you moving? The particle responds with a specific momentum, but it cannot answer both questions simultaneously with perfect precision. The more you pin down one, the fuzzier the other becomes. This is not a limitation of instruments, but a fundamental structure of the universe. The Heisenberg uncertainty principle formalizes this limit. It is not randomness, it is geometry. It tells us that the universe protects certain forms of uncertainty at all times. No matter how hard you try, you cannot force a particle to reveal more information than the rules allow. Observation does not merely change what we know about the particle, it changes what the particle is allowed to be. If you imagine watching a quantum system evolve, it feels a bit like watching a soap bubble shimmer in shifting light. The bubble displays countless colors, each a potential version of itself. But the moment you touch it, even with the gentlest fingertip, the shimmering possibilities vanish. The bubble collapses into a single fragile bead or disappears entirely. Quantum systems behave similarly. Their shimmering multiplicity, their superposed states, exists only when left alone. Interact with them, and the shimmering stops. A single color remains. But why does this happen? What physically causes collapse? Physicists point to entanglement with the environment. When a quantum particle interacts with a measuring device, the device becomes part of the system. Their states become linked. This linkage spreads outward in a chain. The device becomes entangled with its surroundings, its atoms, the photons bouncing within it, and eventually with the rest of the world. As entanglement grows, quantum coherence, the ability to maintain multiple overlapping possibilities, dies away. This process is known as decoherence. It is the quiet thief that steals quantum weirdness from everyday life. Decoherence explains why chairs don't appear in two places at once, why baseballs don't interfere with themselves, why humans behave classically. Our bodies are constantly interacting with trillions of particles, air molecules, photons, vibrations. We are too entangled to ever exist as a wave of possibilities. We are pinned to definite outcomes by sheer scale. At the quantum level, however, decoherence is easily avoided. A single isolated particle, cooled to near absolute zero and shielded from its environment, can remain in superposition for seconds, minutes, or even hours. Under the right conditions, it can behave like a wave across vast distances. But introduce even the smallest disturbance, a stray photon, a vibration from a nearby atom, and collapse becomes inevitable. When collapse occurs, it is instantaneous. It does not need time to propagate. There is no gradual fade from wave to particle. The universe simply selects one outcome and discards the rest. Of course, the discarded possibilities do not vanish in a physical sense. They remain encoded in the mathematical structure of the wave function, but they are no longer accessible to the system that collapsed. Those unrealized futures fall away like gently fading echoes. If you reflect on this, you begin to sense the delicate poetry built into quantum mechanics. The universe is not rigid, it is flexible, fluid, and deeply responsive. At its smallest scales, reality behaves like a question waiting to be asked. Until that question is asked, reality remains open, holding its options lightly. Consider this: when you measure a particle's position, you are not passively observing. You are participating. You are becoming part of the system's evolution. The boundary between observer and observed softens. You are not outside the universe looking in. You are inside it, woven into the same fabric of interactions as the particles you measure. This perspective reveals something comforting. Observation is not a disruption, it is a relationship, a conversation between the part of the universe doing the observing and the part being observed. The more gently you imagine that relationship, the more the observer effect feels less like a cosmic disturbance and more like a quiet rule governing how information flows. The universe does not give up information freely. It reveals it through interaction, and every revelation reshapes the possibilities that came before it. As you sit with this idea, another question begins to rise naturally from its edges. If observation entangles you with a particle, what happens when two particles are entangled with each other? How does the universe behave when two distant particles share one silent, unified state? Let's drift into that mystery next. Part 4. Why do particles move without traveling? Quantum tunneling is one of the strangest forms of motion in the universe. A particle confronted with a barrier it doesn't have enough energy to cross may simply appear on the other side without passing through. To us, this feels impossible. But to the quantum world, the barrier is only a suggestion. Particles flow not only through space, but through probability itself, slipping into outcomes that classical physics forbids. If you drift gently into the quantum world and try to watch this unfold, you quickly realize that tunneling isn't about a particle cheating the rules. It's about the rules being different to begin with. In our everyday experience, a hill is a hill. If you don't have enough energy to climb it, you cannot reach the other side. But at the quantum scale, a particle is not a tiny marble rolling along a path. It is a wave function, a soft distribution of probability that spreads through space like a quiet fog. And fog does not stop abruptly at a boundary. It thins, but it continues. It lingers. It seeps. When a particle approaches a barrier, its wave function extends into that barrier, decreasing but never dropping to zero. This faint tail of probability is the key. If the barrier is thin enough, or the wave function broad enough, there remains a small but genuine chance of finding the particle on the far side. Not because it smashed through, but because probability seeped through even when classical motion could not. In this way, tunneling is not a particle leaping the barrier. It is the barrier failing to eliminate all possibilities. If you could visualize this, it would resemble watching a soft ripple of light approach a wall. Most of the wave reflects back, but a tiny portion penetrates, not as a coherent beam, but as a delicate glow. That glow exists because the wave is not forbidden from being there. It is merely suppressed, and that suppressed presence is enough to allow the particle to appear beyond the barrier. This appearance feels instantaneous. One moment the particle is on one side, the next, it is detected on the other. The journey in between is never observed. In fact, asking, "How long does tunneling take?" is a question that begins to fray at the edges of meaning. A particle in superposition does not move through space the way a classical object does. It transitions between allowed states. The barrier is not broken. The rules are simply written in a language where motion is defined differently. If you try to track a particle during tunneling, the act of measurement collapses its wave function, erasing the tunneling process entirely. This reminds us that quantum motion is fragile, easily destroyed by interaction. The moment you try to watch the transition disappears. This softness, this need for silence, is what gives tunneling its dreamlike quality. Yet, for all its delicacy, tunneling is not rare. It is not exotic. It is not limited to perfectly controlled laboratory experiments. It is happening inside you right now as you breathe. In the nuclear reactions that power the sun, tunneling is essential. Protons inside the solar core repel each other fiercely. Classically, they should never come close enough to fuse. Their electric repulsion forms a barrier far too high. But quantum tunneling gives them a small chance, a tiny window through which fusion can occur. Without this quiet allowance, the sun would be dark. The stars we see across the galaxy would never have ignited. Every beam of starlight that has ever reached your eyes carries the signature of tunneling. And here on Earth, tunneling enables modern technology. In semiconductor devices, electrons tunnel through thin insulating layers to create the basis of memory storage. In scanning tunneling microscopes, the tunneling current reveals the positions of atoms themselves. These microscopes don't touch the surface. Instead, they measure how easily electrons tunnel between the tip and the sample. The result is an image so detailed that individual atoms appear like small glowing points. Tunneling allows us to see the world at a scale light alone cannot reveal. But perhaps the most astonishing example lies not in stars or machines, but in biology. Some of the reactions in your body, particularly those involving enzymes, appear to use tunneling to move protons or electrons across molecular structures. Life, in its most intricate chemistry, relies on the ability of particles to slip through barriers instead of over them. This is not a quirk of physics. It is one of the subtle mechanisms that makes biology possible. If you reflect on this, the strangeness becomes softer. The universe does not permit tunneling to break its laws. Tunneling is one of its laws. It is a consequence of the wave-like nature of matter, a consequence of uncertainty, a consequence of a world built not from certainties, but from distributions of likelihood. To understand tunneling more deeply, imagine confining a particle inside a tiny box. Classically, the particle stays trapped unless enough energy is added to escape. But quantum mechanics allows the particle's wave function to leak into the surrounding walls. If the walls are thin, the particle may escape without ever having the classical energy required. The box is not truly confining, it merely lowers the probability of escape. Given enough time, escape becomes inevitable. This quiet inevitability is one of the universe's most elegant compromises. At small scales, nothing is truly absolute. Barriers have thickness, boundaries have softness, certainty has limits. The quantum world is not bound by rigid edges, it is bound by probability gradients. If you sit with that thought, you may begin to sense the philosophical weight of tunneling. It suggests that obstacles are not final. They are regions of lowered likelihood, not walls carved into reality. Even in the language of physics, impossibility is often replaced by improbability. Tunneling also reveals something profound about the relationship between energy and space. In classical mechanics, not having enough energy means stopping. But in quantum mechanics, energy is not the sole determinant of motion. The shape of the wave function matters too. A broader wave function increases the probability of tunneling. A narrower one reduces it. Thus, motion becomes not a question of force, but of form, of how a particle's probability spreads, evolves, and interacts with its surroundings. This interplay is delicate. A slight change in the barrier's width or height can alter tunneling rates by orders of magnitude. This sensitivity is why tunneling can operate as a switch in electronics, and why stars depend on it with razor-thin precision. The quiet fate of a universe filled with light hinges on probabilities that feel almost impossibly small, yet accumulate across trillions of particles every second. There is a quiet beauty in this. The universe runs on chances that are gentle but constant. And like all quantum phenomena, tunneling sits at the intersection of two worlds, the world of waves and the world of particles. The wave allows the particle to explore forbidden regions. The particle gives the wave meaning by becoming one definite outcome afterward. Tunneling is not a violation of classical motion, it is motion as understood by quantum rules, where presence is not limited by energy alone, but is guided by the spread of possibility. As you drift away from this segment, holding the image of a particle appearing on the far side of a barrier it never crossed, you may feel the next question rising gently from within this mystery. If particles can slip through barriers by exploring possibility, what happens when their identities themselves become fuzzy? What does it mean for a particle to possess a spin that is not a rotation or an orientation that exists in multiple forms at once? Let us continue to Part 5. Part 5. What does it mean for something to spin without spinning? Every fundamental particle has a property called spin, yet it is not a physical rotation. Instead, it is an intrinsic form of angular momentum woven into the particle's identity, a quiet fingerprint of quantum behavior. Spin determines how particles align, how they pair, and how matter itself forms. It's a rotation that exists in mathematics rather than motion, a reminder that quantum rules are deeper than intuition. If you drift into the quantum world, the first thing you discover is that many familiar terms do not survive the journey unchanged. Words like spin, momentum, position, and direction carry deep classical meaning in our everyday lives. We know what it means for a planet to spin, for a dancer to turn, for a wheel to rotate. But a particle's spin is not that. If you imagined a tiny electron twirling like a microscopic top, you would be pulling intuition from the wrong world. An electron is not a sphere. It has no surface. It has no edges or ridges. It is not made of smaller parts that could rotate. And yet it has angular momentum, real, measurable, angular momentum. This is the first sign that spin belongs to a category of ideas that have no classical counterpart. It is a property we must accept on its own terms, without leaning on pictures borrowed from the macroscopic world. If you could watch an experiment sensitive enough to detect spin, you'd see that it behaves more like a magnetic orientation than a physical rotation. Particles with spin interact with magnetic fields. They tilt, they align, they split into distinct paths when passed through inhomogeneous fields. These behaviors are exactly what you would expect from tiny magnets, not tiny spinning balls. The most famous demonstration of this is the Stern-Gerlach experiment, performed in 1922. A beam of silver atoms was passed through a magnetic field with a gradient. Classically, one would predict a continuous spread of deflected atoms, some pointing slightly up, some slightly down, forming a smooth smear on the detector. But that isn't what happened. Instead, the atoms separated into two clean, distinct spots, two possible orientations, no middle ground. This was the first direct evidence that spin comes in discrete quantum values, not continuous ones. There is no in-between, no gentle slope, only quantized options, up or down, plus 1, 2 or 1, 2, a binary nature written into the heart of matter. This discreteness is what makes spin so deeply quantum. It does not emerge from geometry, it emerges from symmetry, mathematical symmetry in the abstract structure of space itself. If you imagine slowly rotating an electron, not physically but conceptually through mathematics, something remarkable happens. When you rotate a classical object by 360 degrees, it returns to its original state. But rotate an electron's wave function by 360 degrees, and it does not return to its original state. It flips sign. It becomes the negative of itself. You must rotate it 720 degrees, 2 full turns, to restore it. This strange requirement has no classical analogy. Nothing in everyday life behaves this way. But in quantum mechanics, it is a natural consequence of being a spin 1-2 particle. The fact that electrons require 2 rotations to return to their initial state is more than a curiosity. It reveals something profound. Spin is tied to the underlying geometry of spacetime. It emerges from how particles transform under rotations in that geometry. It is woven into the very structure of the universe's mathematical fabric. Spin also influences how particles occupy space. Electrons, protons, neutrons, and quarks all have half-integer spin. They belong to a class of particles called fermions. Fermions obey the Pauli exclusion principle. No 2 identical fermions can occupy the same quantum state. This single rule is responsible for the structure of the periodic table, the stability of atoms, the existence of chemistry, and even the solidity of matter. Without it, electrons would collapse into the atomic nucleus, atoms would flatten into uniform blobs, and the world would have no texture. Spin is the quiet architect of form. Particles with integer spin, photons, gluons, the Higgs boson, are bosons. Bosons have no exclusion principle. They can pile into the same state, move in unified waves, and behave collectively. Lasers exist because photons share the same quantum state. Superfluid helium flows without friction because bosons condense into a single quantum wave. These behaviors are not possible for fermions. Their spins forbid it. Thus, the spin of a particle shapes whether it seeks individuality or unity, whether it forms matter or mediates forces, whether it stands alone or merges with others. As you move deeper into this idea, you realize that spin is not just a number in an equation. It is a pillar of the universe's architecture. It tells particles how to behave, how to interact, how to bind, how to assemble. It is the rule that gives the universe its texture, its hierarchy, its diversity. Spin is also connected to magnetic moments. The electron, for instance, has a magnetic moment slightly different from what simple equations predict. This tiny discrepancy, one of the most precisely measured quantities in physics, has been confirmed to over a dozen decimal places. The level of agreement between theory and experiment stands as one of the greatest achievements of quantum electrodynamics. It shows that spin is not an abstraction. It is a measurable, concrete property with real consequences. If you used a scanning technique sensitive enough to map the magnetic field of a single electron, the orientation you observed would be defined by its spin. Its alignment or anti-alignment with an external field would dictate how it behaves, how it shifts energy levels, how it interacts. That tiny tilt, quantized in binary, is responsible for phenomena ranging from MRI machines to the magnetic behavior of stars. Spin also plays a role in entanglement. When two electrons form a bonded pair in an atom, they do so by arranging their spins in opposite directions. One spin up, one spin down. This pairing allows them to occupy a shared orbital without violating the exclusion principle. In metals, electrons with opposite spins can form Cooper pairs, allowing them to move without resistance in a superconducting state. In these moments, spin becomes a quiet coordinate of identity, dictating how particles cooperate. If you continue drifting through this quantum landscape, watching spin-guide interactions like a silent compass needle, you may begin to notice something more philosophical. Spin is not rotation, it is orientation within possibility. It is a kind of directionality that exists even when the particle has no size, no surface, no classical shape. It is an intrinsic property, not a motion. It is the universe saying, this is how this particle participates in symmetry. And in physics, symmetry is not decoration, it is law. It tells particles how to transform, how to conserve angular momentum, how to interact with fields, how to fit into the larger pattern. Spin is therefore part of the rulebook that governs existence. It is not optional. It does not emerge from motion. It emerges from the deep algebraic structure underlying spacetime. If you take a slow breath and reflect, you might realize that spin explains something profound about why matter is stable, why atoms do not collapse, why stars shine, why the universe has layers instead of being a single uniform soup. Without spin, the world would be shapeless and featureless. With it, the cosmos is structured, diverse, and dynamic. As you prepare to leave this chapter behind, another question begins to rise softly from the edge of this exploration. If particles carry these intrinsic orientations, how can they influence each other instantly across great distances? What happens when spin becomes shared, when two particles behave as one, no matter how far apart they drift? Let us drift now toward that mystery. Part 6. Why do particles influence each other instantly? Quantum entanglement links particles across distance in a way that defies classical separation. When two particles become entangled, their states mirror each other no matter how far apart they drift. Change one, and the other responds instantaneously. Einstein called this spooky action at a distance, but today we understand it as a fundamental feature of quantum information, correlation without communication, woven into the fabric of reality. To understand entanglement, imagine watching two particles interact and then drift apart. At the moment of their interaction, whether through collision, emission, or shared origin, their properties become correlated. Their spins, momenta, or polarizations become part of a single quantum description. After that moment, the universe no longer treats them as separate. They are described by one wave function, one mathematical entity extending across both particles. Even if you separate them by miles, they remain part of the same quantum system. If you drift gently inside this idea, you begin to notice something subtle. Entanglement is not about sending messages faster than light. The particles do not communicate. They do not send signals through space. Instead, they share a state in which the outcome of one measurement is inseparable from the outcome of a measurement on the other. The correlation does not travel. It is simply there, a built-in structure of their relationship. In this sense, entanglement is not spooky at all. It is a quiet form of unity. Imagine two coins that always land on opposite sides, heads for one, tails for the other. But now imagine that instead of being classical coins with fixed faces, they exist in quantum superposition. Each coin is both heads and tails until observed. And when you finally look at one, the outcome instantly determines the state of the other, no matter how far away it is. It is not that the second coin changes in response, it is that the universe never allowed their states to be independent in the first place. Quantum mechanics does not store information in individual particles. It stores information in relationships. If you visualize the wave function of two entangled particles, it does not split cleanly into two separate waves. Instead, it stretches like a shared fabric, with ripples on one side instantly reflected on the other. Not because something travels across the fabric, but because the fabric is one connected piece. This is why locality breaks down at the quantum scale. Not because information travels faster than light, but because the distance you imagine between particles is not a barrier inside the mathematics. The wave function is non-local. It is a single object extending across space. Entanglement also shows up in the conservation of angular momentum. Consider a particle with spin 0 that decays into two particles, each with spin 1/2. Because the total must remain 0, the two resulting spins must be opposite. But until measured, neither particle has a definite spin. Each exists in a superposition of up and down. Only the combined state is definite. The total is 0. When you measure one particle and find its spin up, the other must be spin down to preserve the total. This is not communication. It is bookkeeping. And the ledger is written at the moment of entanglement. If you travel deeper into this concept, you find that entanglement is not fragile in the way intuition suggests. It can survive great distances. It can persist across light years if isolated from the environment, but it is sensitive to interaction. The moment either particle becomes entangled with something else, an atom, a photon, a measuring device, the original pair's entanglement is diluted or lost. This process, known as decoherence, prevents entanglement from scaling to macroscopic levels. That is why you never see two large objects exhibiting mirrored quantum states across space. Their complexity makes perfect entanglement effectively impossible. But even with these limitations, entanglement is astonishingly powerful. It is the foundation of quantum cryptography, where two parties share entangled photons to ensure that any attempt at eavesdropping collapses the system and reveals the intrusion. It underpins quantum teleportation, a protocol in which the state of a particle can be transferred to another particle across distance, not the particle itself, but the information that defines it. Teleportation works not by sending matter faster than light, but by consuming entanglement as a resource. The entangled pair acts like a bridge between states. When you measure one particle in a certain way, you collapse not just its own possibilities, but also its partners. With additional classical communication, the receiving particle can be transformed into the original state of the sender. Nothing physical travels, only information, and even that information obeys the speed limit of light, so entanglement does not break relativity. It honors it in quiet, surprising ways. If you zoom out and reflect, you begin to see entanglement everywhere. Photons emitted from the same atom often leave in entangled pairs. Electrons in certain materials move in entangled waves. The chemical bonds that hold molecules together rely on entangled electrons. Even the structure of superconductors and exotic quantum phases of matter are built on webs of entanglement stretching through vast numbers of particles. This raises a gentle philosophical question. If entanglement can link particles across infinite distances, could the entire universe be connected through some ancient network of correlations formed in the first moments after the Big Bang? Some physicists believe so. The early universe was small, dense, and hot, perfect for entanglement to occur on a massive scale. As the universe expanded, these correlations may have stretched with space itself, creating a faint, invisible lattice of quantum relationships. We cannot observe these directly, but hints appear in cosmology, in the uniformity of the cosmic microwave background, and in certain models of quantum gravity that propose space-time itself may emerge from patterns of entanglement. In these theories, space is not fundamental. It is a consequence of how quantum information arranges itself. Distance is an illusion built on relationships, and entanglement is the thread from which the fabric of space-time is woven. Even if these ideas remain theoretical, they point to something deeply comforting. The universe is more connected than it appears. Separation is a classical illusion. At its foundations, reality is relational. Particles are not isolated points, but participants in shared states. Their identities are tied to each other, shaped by interactions and defined by symmetries. If you drift a little closer to the emotional texture of this truth, it feels less like physics and more like perspective. That the universe, at its smallest scales, does not behave as a collection of isolated objects, but as an interdependent whole. The instant correlations of entanglement, the mirrored states, the unity across space, all of these hint at a cosmos where relationships precede individuality. As this chapter settles, another quiet question begins to rise, gently and naturally. If entanglement binds particles through relationships, what happens when the space between them is empty? What does the vacuum itself contain, and why is emptiness never truly empty? Let us drift into that mystery next. Part 7. Why do quantum particles refuse to sit still? Even at absolute zero, where all classical motion should cease, quantum particles continue to jitter with a faint, irreducible hum known as zero-point energy. This restless motion is not noise but requirement, a baseline vibration of the universe. It's the quiet reminder that emptiness is never empty, and stillness is never truly still. If you drift gently into the quantum world, the first thing you notice is how the concept of zero begins to dissolve. Zero temperature, zero energy, zero motion. These classical ideas feel crisp and absolute to us. They work well on human scales. When something cools down, its atoms slow. When it freezes, they slow further. And in our imagination, if we could cool something all the way to absolute zero, minus 273.5 degrees Celsius, all motion would stop. Particles would settle into perfect silence, but the universe does not allow such stillness. Nature forbids it at the smallest scales. The reason lies in a principle woven into the foundation of quantum mechanics, the uncertainty principle. According to this rule, a particle cannot have both a precisely defined position and a precisely defined momentum at the same time. The more tightly you try to pin down one, the more uncertain the other becomes. And perfect stillness, motion equal to zero, would require perfect knowledge of both. It would violate the universe's built-in uncertainty. So instead of lying motionless, every particle retains a tiny amount of irreducible vibration. Even in the coldest conditions humans have ever created, fractions of a billionth of a degree above absolute zero, atoms still quiver softly. They do not drift from place to place, but their wave functions fluctuate, spread, compress, and shift. This is not thermal motion, it is deeper, it is structural, it is the signature of the quantum world. Zero-point motion is like the heartbeat of matter. This motion becomes clearer when you imagine a particle trapped inside a tiny container, a quantum well. Classically, the lowest energy state would be simple. The particle rests at the bottom, unmoving. But quantum mechanics tells a different story. If the particle were perfectly still, we would know its exact momentum, zero. That violates uncertainty. So instead, the lowest state, called the ground state, has a small, unavoidable energy. The wave function spreads across the well. The particle jiggles not because it wants to, but because it must. This hum of zero-point energy shows up everywhere. In solid crystals, atoms vibrate even at zero temperature. These vibrations create phonons, quantized packets of sound. Phonons exist because the crystal's atoms cannot lock themselves into motionless perfection. They continue to sway in coordinated patterns, a silent music played beneath the threshold of matter. If you could shrink down and stand among these atoms, you would not see a rigid lattice frozen in silence. You would see something closer to a field of gently trembling lights, each atom a soft, quivering point, its probability cloud pulsing with quiet regularity. The entire structure would shimmer faintly, even in perfect darkness. Zero-point energy is not just a quirk. It shapes the universe in profound ways. For example, helium remains liquid all the way down to absolute zero unless compressed. This is because zero-point motion prevents helium atoms from settling into a rigid solid lattice. Their jitter is too strong. The atoms slip past each other even when cooled to unimaginable levels. Only by applying pressure, forcing the atoms close enough that their interactions overwhelm their quantum motion, can helium be frozen. This is why liquid helium can creep up the sides of containers and form frictionless films. Its atoms are so light and so dominated by zero-point motion that they behave in ways no classical liquid ever could. Another example lies in the Casimir effect, a subtle force that appears between two metal plates placed extremely close together. Classically, there should be no force, but quantum fields filling the vacuum between the plates are restricted in the wavelengths they can support. Outside the plates, all wavelengths exist. The mismatch in zero-point energy creates a slight pressure difference, pushing the plates together. This tiny force, measured in laboratories, is a direct consequence of the restless quantum vacuum. Even the structure of atoms themselves depends on zero-point motion. Electrons do not collapse into the nucleus because their wave functions spread out, maintaining a finite size. This spreading requires kinetic energy. If electrons were allowed to be perfectly still, atoms would shrink into singular points. Zero-point energy prevents this collapse, giving atoms their volume and the material world its scale. In a quiet sense, the very space you occupy, everything you touch, everything you breathe, is shaped by motion that never stops. If you drift deeper into the mathematics, zero-point energy arises from the quantization of fields. Every field in the universe, whether describing particles of matter or force-carrying bosons, behaves like a harmonic oscillator. And quantum harmonic oscillators cannot have zero energy. Their lowest state is always half a quantum of energy. Multiply this by every mode of every field, and the vacuum becomes a seething background of fluctuations. These fluctuations appear and disappear. They create virtual particle pairs that flicker into existence and annihilate each other almost instantly. They tug on boundaries. They shift atomic energy levels. They generate measurable forces. This constantly bubbling vacuum underlies the entire structure of reality. If you could float inside a pure vacuum, a region stripped of particles, of light, of heat, you might imagine yourself drifting through emptiness. But quantum mechanics tells us you would not be alone. The vacuum hums with activity. Waves rise and fall. Virtual particles swirl in pairs. The energy never drops to zero. Stillness is an illusion created by scale. Zero-point motion also influences the universe on the largest scales. In cosmology, the energy of the quantum vacuum may relate to dark energy, the mysterious force accelerating the expansion of the universe. Although the connection is not yet fully understood, the idea that the vacuum itself carries energy, a pressure that cannot be removed, echoes the quiet truth that nothingness is never truly nothing. This brings us to a gentle philosophical realization. The universe itself refuses to sit still. Not because it is restless, but because fundamental uncertainty is built into its fabric. Motion, vibration, fluctuation, these are not imperfections. They are requirements. They are the natural breathing of the quantum world. If you pause and breathe with this idea, you begin to sense its emotional weight. The smallest components of reality are never frozen, never stuck, never perfectly at rest. They shimmer with possibility, with inevitable motion, with the quiet pulse of existence. Even in the coldest imaginable place, even in the emptiest region of space, there is always a gentle murmur beneath the silence. This murmur supports matter. It shapes space. It guides interactions. It is the background hum of reality. And as you begin to leave this chapter, another question rises softly from the threshold of this quantum landscape. If emptiness is filled with motion and stillness is an illusion, what happens when particles behave not like points at all, but like waves spreading through space? Let's drift into that mystery in the next part. Part 8. Why do particles sometimes act like waves? In the quantum world, particles are not tiny marbles, they are wave functions. Electrons diffract, photons interfere. Particles create fringes like ripples on water. Their behavior depends on how we measure them, shifting seamlessly between wave-like and particle-like identities. This duality is not a trick, but the essence of quantum behavior, matter and energy refusing to choose a single form. If you drift slowly into the quantum realm, the very first impression you feel is this strange softness. Nothing has sharp edges, nothing has a strict outline. Instead of objects with clear boundaries, you find waves, patterns of probability, spread through space like quiet vibrations. These waves are not metaphorical. They are real, measurable, and essential. They shape how electrons arrange themselves in atoms, how photons travel through space, how matter behaves at its tiniest scales. To understand why particles act like waves, imagine watching a single electron approach a narrow slit in a barrier. In the classical world, the electron would hit the barrier or pass cleanly through the opening. But in the quantum world, the electron's wave function spreads out. As it passes the slit, it diffracts, bending, curving, expanding, just as a wave of water would when flowing past a rock. If you place a screen behind the slit and repeat the experiment many times, the electrons land in a pattern of bright and dark bands. These interference fringes are not created by multiple electrons pushing each other. Each electron creates the pattern alone. This is the signature of wave behavior. It reveals that the electron is not a localized point choosing a single path, but a wave function exploring many paths simultaneously. If you add a second slit, the pattern becomes even more striking. The electron's wave function passes through both openings at once, overlapping with itself, interfering with itself. Peaks of probability amplify each other, valleys cancel out. The result is a beautiful pattern of alternating bright and dim stripes, an interference pattern that can be seen even when electrons are fired one at a time, minutes apart. To understand how profound this is, imagine dropping a single pebble into a still pond and seeing ripples not only where the pebble lands, but across the entire surface, forming patterns you cannot create with just one disturbance. This is what particles do. They generate a pattern of possibility that behaves like a wave, not a point. Yet if you place detectors at the slits to determine which path the electron took, the interference pattern vanishes. The electron behaves like a particle again. It chooses one slit or the other. The wave-like behavior collapses under observation. This is not because the electron changes its mind. It is because measuring its position requires an interaction. Any interaction, even the smallest exchange of information, forces the wave function to collapse into one of its particle-like configurations. Wave-particle duality is not a flaw in our descriptions. It is the universe revealing that the classical categories of particle and wave are inadequate. At the quantum level, these categories merge. A particle is a quantum object, and quantum objects have properties of both. If you drift further, you begin to see wave functions everywhere. In atoms, electrons do not orbit the nucleus like planets around the sun. Instead, they exist in standing waves, stable patterns of probability that form shells. Each shell represents a specific energy state. Each has a shape: spherical, dumbbell-shaped, ring-shaped. These shapes are not imaginary. They can be measured, they can be visualized, they define chemistry. The periodic table itself emerges from these waveforms. When you touch anything, wood, metal, water, the solidity you feel arises from wave functions refusing to overlap. Your hand does not pass through the table because the electron waves in your skin interfere with the electron waves in the table. Matter resists compression because wave functions repel when squeezed too closely. This is why atoms have size, why molecules have shape, why the world does not collapse into a dense, featureless soup. Wave behavior provides structure. If particles acted only like particles, atoms would be unstable. They would collapse inward. Electrons would spiral into the nucleus. Molecules would not form. The universe would have no chemistry, no stars, no life. Wave-like behavior is not optional. It is essential. Photons, too, exhibit duality. Light travels as a wave, spreading smoothly across space. But when it interacts with matter, when it hits a detector or strikes a molecule in your eye, it behaves like a particle, delivering energy in discrete packets called quanta. This dual nature allows lasers to be coherent light waves while also enabling the photoelectric effect, where individual photons liberate electrons from metal surfaces. Even heavier particles, protons, neutrons, atoms, and entire molecules have been shown to exhibit wave-like properties. In experiments, scientists have diffracted molecules as large as fullerenes, complex structures containing dozens of atoms. When cooled and isolated, even these large molecules generate interference patterns. They act like waves until observed. Wave-particle duality scales up more than intuition suggests. If you could see the wave function of a single atom, it would not appear as a tiny dot. It would look like a soft, glowing cloud, its brightness showing the likelihood of finding the atom in each location. This cloud would pulse gently over time, shifting shape with changing energy states. It would be beautiful, like watching a lantern drifting underwater, casting shifting patterns of light through a dark sea. These patterns of possibility are not static. They evolve according to Schrödinger's equation, which tells how wave functions change with time. This equation is the quantum version of Newton's laws, describing not definite trajectories, but the flow of probability. Under its guidance, wave functions stretch, compress, split, merge, and interfere, behaviors impossible for classical particles. The beauty of duality is that it does not create contradiction. It creates completeness. Particles behave like waves because waves describe the fullest version of their behavior. And they behave like particles when forced into one of their many possible configurations by measurement. The universe does not choose one or the other. It chooses both. If you reflect on this quietly, a philosophical truth emerges. Quantum objects are defined not by a single identity, but by a palette of possible identities. They inhabit a space of potential until something interacts with them. Waves allow them to explore possibilities. Particles express the outcomes. The duality is not a conflict, it is a harmony. Wave-particle duality also plays a role in how electrons move through solids. In a metal, electrons behave like extended waves spanning the entire lattice. They move not as individuals, but as collective patterns. This is why electricity flows smoothly. In semiconductors, wave functions determine which energies electrons can occupy, enabling the digital world. The quantized energy bands of solids are wave phenomena, not particle phenomena. Even the behavior of particles in magnetic fields is wave-like. Electrons form discrete orbits known as Landau levels when placed in strong magnetic fields, a phenomenon entirely explained by wave equations. In many of these systems, the wave nature of matter creates emergent properties far from intuitive: superconductivity, superfluidity, quantum Hall effects. All arise from waves interacting, reinforcing, canceling, or aligning. When you step back from all of this, another truth becomes clear. Wave-particle duality is not an oddity of nature. It is the blueprint of nature. Matter and energy behave like waves because the universe is built not from fixed objects, but from fields, extended entities that span space. Particles are excitations in these fields, ripples of energy that behave like both waves and particles, depending on how they are asked to reveal themselves. As you drift out of this chapter, a new question begins to rise softly from within the calm complexity of duality. If particles are waves spread across space, what happens when we look inside one? What lies within a proton or neutron, and how does the wave-like behavior of its constituents shape the world? Let us explore that mystery next. Part 9. What is hiding inside a proton? Protons, once thought solid and indivisible, are now known to contain quarks and gluons locked in constant turbulent motion. Deep inelastic scattering experiments showed that protons behave less like spheres and more like storms, fields of energy whirling in confinement, never sitting still. At this level, structure is fluid, motion is constant, and even particles feel more like patterns than objects. If you drift down into the heart of matter, past atoms, past the empty space within atoms, past even the swirling electron clouds, down into the nucleus, you find a world unlike anything you've imagined. The proton is not a marble. It is not a bead or a ball. It's not a tiny solid thing waiting at the center of the atom. Instead, what you find is a storm of energy so intense, so restless, that the very idea of inside becomes blurry. Boundaries dissolve, motion blurs, and the proton becomes less of an object and more of a process. Early scientists believed protons were indivisible. They were wrong, but the truth is far stranger than simple division. When experiments at SLEC in the late 1960s and early 1970s blasted protons with high-energy electrons, the electrons didn't bounce off the proton's surface. They scattered in patterns that revealed internal structure, hard, point-like constituents hidden inside. These constituents were eventually recognized as quarks, and the force binding them, the glue holding the proton together, comes from massless particles called gluons. But the name gluon is misleadingly gentle. Gluons do not simply stick things together. They create a churning sea of energy, an ever-changing mesh of color charge, rippling in ways that defy classical intuition. This churning is described by quantum chromodynamics, the theory of the strong force. It is the strongest force in the universe, billions of times more powerful than electromagnetism, and it keeps quarks confined so tightly that they can never escape the proton on their own. As you descend deeper into this subatomic weather system, the quarks themselves appear strange. They are not stable beads of matter. They flicker and jitter, exchanging gluons constantly, pulling and pushing in a chaotic dance. The three valence quarks, 2 up quarks and 1 down quark, that define the proton's identity are only a small part of the story. Surrounding them is a roiling sea of virtual quarks and antiquarks, constantly appearing and vanishing, created by the energy of the gluon field itself. Inside the proton, existence is dynamic. Everything changes, all the time. If you try to visualize this interior, imagine a storm cloud in slow motion, not made of water vapor, but of pure energy. Within it, bright sparks flash, the quarks, connected by twisting, vibrating strands of light-like tension, gluons. The strands stretch and compress, storing enormous energy, because in quantum chromodynamics, the more you try to separate quarks, the stronger the pull between them becomes. Unlike gravity or electricity, the strong force does not weaken with distance. It tightens, it resists, it traps. This phenomenon, confinement, is one of the strangest in physics. You can never isolate a single quark. Pull 2 quarks apart, and the energy between them grows until it becomes more favorable for the universe to create a new quark-antiquark pair than to let the original one separate. The proton's interior is a constant act of creation, annihilation, recombination, a swirling ocean of quantum motion that never rests. If you drift through this chaos, what you feel is a kind of organized disorder. Quarks dart in and out of existence so quickly that they cannot be seen directly. Gluons radiate energy like vibrating strings, binding the quarks, but also binding each other. Even the empty spaces within the proton are alive with fields. Every region pulses with fluctuations. This is why scientists often say that the mass of a proton does not come from the quarks inside it. In fact, quarks account for only about 1% of the proton's mass. The other 99% comes from pure energy, the kinetic energy of the quarks and the potential energy of the gluon field. Mass in this context is not something the proton has, it is something the proton does, a dynamic aggregation of motion and force. If you expand your view slightly, you find that this storm has structure. The proton's spin, for instance, does not come from the spin of its 3 valence quarks alone. In fact, experiments have shown that quarks contribute only a small fraction of the proton's total spin. The rest comes from the motion of gluons, from orbital angular momentum within the storm, from the swirling patterns of fields. The proton's rotation is a collective phenomenon, emerging from the combined behavior of countless internal components. This realization changed our understanding of matter forever. The proton is not a tiny piece of the universe's building material. It is a dynamic system, a miniature cosmos of forces interacting in ways that are deeply nonlinear and profoundly beautiful. If you float deeper still, you encounter something even more surprising. The proton has no single, fixed shape. At high energies, it looks like a pancake, a flattened distribution of gluon density. At lower energies, it looks more spherical. Probe it at different interaction strengths, and you reveal different structures. Sometimes 3 bright cores, sometimes a smeared cloud, sometimes something more like a fractal of energy. Distribution than an object with a stable boundary. The proton changes depending on how you ask your question. This reflects a core truth of quantum mechanics. The observer shapes what is observed. The proton is not one thing. It is many things, many forms, emerging from the conditions of measurement. Scientists map these forms using deep inelastic scattering, lattice QCD simulations, and models of parton distributions. Each technique reveals a different layer of truth, a different aspect of the swirling interior. But none of these layers exist in isolation. All of them are real. All of them coexist. As you watch this storm, you begin to understand why particles feel like patterns rather than objects. A particle is not a nugget of matter. It is a region of space where fields are vibrating in specific quantized modes. A proton is a stable resonance in the quantum fields that permeate the universe. It persists because its internal dynamics reinforce each other. The motion inside does not tear it apart. The turbulence binds it. What should be chaos becomes harmony. And that harmony forms the foundation of everything you know. Every atom in your body, every carbon nucleus, every oxygen nucleus, every nitrogen nucleus is held together by protons and neutrons that behave this way. Each of them contains similar storms of quarks and gluons, each a miniature hurricane of energy, each obeying the same strange laws. You are built from these storms. Everything in the world is built from them. This realization brings a quiet awe. You are the calm surface of an unimaginably complex ocean. Beneath every solid thing is a swirling, shifting world where even particles are dynamic patterns of motion. Inside, every proton is a tiny universe, alive with energy. And as you drift gently away from this turbulent landscape, another question begins to rise from the edges of the storm. If particles are made of patterns and motion rather than matter, how do they know all the possible paths they could take? Let us drift into that mystery in the next part. Part 10. How does a particle know every path it could take? In quantum mechanics, a particle doesn't choose a single trajectory. Instead, it explores all possible paths simultaneously, each contributing to the final outcome. This idea, Feynman's path integral formulation, reveals a universe where every potential route matters. Motion becomes a sum of possibilities, not a single thread, but a woven tapestry of might-have-beens. If you drift gently into this chapter of the quantum world, the first thing you feel is that motion is no longer what it seems. In the classical world, motion is a clean story. An object begins here, ends there, and carves a single line through time to bridge the two. You can trace its trajectory with certainty. There is one path, one history, one record of how the object moved. Quantum mechanics unravels this certainty. At the microscopic scale, a particle does not simply travel along one path. It explores all paths. Every route, every detour, every wandering curve through space and time carries a contribution to the final outcome. According to Feynman's formulation, the particle's behavior arises from the interference of all these possibilities. Some paths add together, some paths cancel, some dominate, some whisper faintly in the background. The particle's final location is not the result of a single journey, but the resonance of all the journeys it could have taken. If you could witness this directly, it would feel like watching a ghost walk every possible road at once. One ghost steps forward in a straight line, another arcs to the left, another wanders, another loops around obstacles, and countless more take routes so strange that they defy classical description. Each ghost leaves a faint imprint. The imprints overlap and interfere, producing the final probability pattern that determines where the particle is likely to appear. In this picture, motion is not a single thread. It is a tapestry woven from infinitely many strands. The beauty of the path integral approach is that it doesn't ask the particle to decide. It doesn't force nature to choose prematurely. Instead, it allows all allowed histories to coexist until the moment a measurement collapses them into one outcome. But beneath the collapse, the sum of these histories still guides the particle's behavior. This is why particles show interference patterns. The paths interfere with one another, just as waves do. Paths that reinforce create regions of high probability. Paths that cancel create regions of low probability. The particle does not know the best route in advance. It explores everything and lets the mathematics of interference determine what we observe. Here, the universe begins to feel less like a machine and more like a poem. To understand this more deeply, imagine throwing a pebble into a pond. The ripples travel outward, overlapping, reinforcing, and canceling. The resulting pattern is not simply the sum of the ripples, it is the interference of all possible ripples. The path integral formulation applies this idea to motion itself. A particle is not a dot carving out a line. It is a wave exploring all its potential paths and letting the structure of the wave define where it is likely to be found. This brings us to a profound realization. Quantum motion is not deterministic in the classical sense. It is informational, probabilistic, harmonious. The particle does not know every path in the conscious sense. Rather, the laws of physics allow all paths to contribute, and the mathematics naturally selects the ones that matter most. Paths that are wildly different from the classical trajectory tend to interfere destructively. They cancel. Paths that are close to the classical trajectory tend to reinforce. They dominate. This is how classical motion emerges from quantum motion. It is not imposed from the outside. It emerges from the sum of many possibilities. If you reflect on this, the quiet beauty becomes clear. The straight line path we see at macroscopic scales is not the only possibility. It is simply the one that remains after countless other histories cancel out. In this sense, classical reality is the shadow cast by a deeper, more intricate quantum truth. If you drift deeper into this idea, you discover that the particle's path is not just a sum of different spatial routes. It is a sum of different ways the universe could evolve between two events. In the path integral picture, time is not a rigid sequence. It is a field of potential histories. Every moment is shaped by many possible trajectories, all contributing to the final tapestry of outcomes. This picture explains phenomena that classical physics struggles with. Tunneling, for instance, arises naturally in the path integral view. A particle may not have enough energy to cross a barrier along the classical path, but non-classical paths, ones that curve through forbidden regions, still contribute. They do so faintly, but not zero. And because the final outcome includes all contributions, the particle sometimes appears on the other side. Quantum motion becomes a conversation between what is likely and what is allowed. Another beautiful example is the Aharonov-Bohm effect, where particles are influenced by electromagnetic fields even when they never pass through the field itself. In the path integral picture, the field changes the phase of the paths, altering how they interfere. The particle does not need to be in the field, its possibilities do. The accumulated phase shift across many paths changes the final outcome. This is the quantum world whispering. Possibility is as real as actuality. If you could see all the paths at once, it might look like a glowing web stretching through space and time. Some strands would shimmer brightly, paths with strong contributions. Others would dim and flicker, paths that cancel or nearly cancel. Altogether, they form the wave function's evolution. Altogether, they shape reality. And yet, when you measure the particle, you see only one result, one position, one momentum, one outcome. The infinite tapestry collapses into a single thread, but that thread carries the imprint of all the other possibilities that were allowed to exist. In this sense, every particle's motion carries memory, not conscious memory, but structural memory, of histories that never fully happened in the classical sense, but shaped what did happen. This is why quantum mechanics feels philosophical. It suggests that reality is built not from events alone, but from the space of events that could have occurred. The particle knows every path in the same way water knows every possible way to flow through a riverbed. It does not choose. It feels the entire landscape. Every shape, every curve, every obstacle contributes to the final pattern of flow. A quantum particle's flow is similar but richer. It is not shaped by physical geography. but by the geography of possibility. Each potential path is a ridge or valley in this landscape. The final motion arises from the interplay of all of them. And as you drift out of this chapter, holding this image of infinite ghost paths guiding a single outcome, another question rises softly and naturally. If particles explore all possibilities, what lies in the space where no particles exist at all? What's the nature of emptiness itself, if even possibility vibrates within it? Let us drift into that mystery in the next part. Part 11. Why does empty space generate particles? Vacuum fluctuations show that what we call empty space is filled with ephemeral pairs of particles appearing and vanishing in tiny bursts of energy. At small scales, space-time behaves like a shimmering ocean of momentary creation. These virtual particles leave measurable imprints, proving that emptiness is alive with structure and activity. If you drift gently into this idea, the first thing you must let go of is the classical notion of emptiness. For most of human history, we imagined empty space as a perfect void, a backdrop with no content, no motion, no form, a silent stage upon which the universe performs. But quantum mechanics replaces that quiet simplicity with something far stranger and far more alive. The vacuum, according to quantum field theory, is not the absence of everything. It is the lowest possible energy state of a field, and every field, electromagnetic, gravitational, Higgs, has fluctuations even in its lowest state. These fluctuations are not artifacts of measurement. They are not noise from our instruments. They are built into the mathematics. They arise from one of the universe's most fundamental truths. Even nothing cannot be perfectly still. The uncertainty principle forbids a field from having exactly zero energy, just as it forbids particles from having exactly zero motion. If a field were perfectly still, we would know both its value and its rate of change with absolute precision, and that is impossible. So instead, the vacuum seethes softly, fields jitter, energy drifts in tiny oscillations, and from these oscillations, virtual particles appear and vanish. If you could see this directly, if you could shrink yourself down until space-time itself looked granular, you would witness a restless landscape. Tiny specks flicker into existence, a particle and its antiparticle paired like twins. They emerge from the energy of the vacuum, exist for a fleeting moment, and then annihilate each other, returning their borrowed energy to the field. They do not persist long enough to be observed as real particles, but they leave behind footprints, shifts in forces, tiny pushes, subtle changes in behavior. The vacuum behaves less like an empty void and more like a sea whose surface is always trembling. Physicists call these ephemeral excitations virtual particles. They are not particles in the traditional sense. They cannot be isolated or detected directly. But they exert influence, they mediate forces, they shape the structure of atoms, they shift energy levels, they appear as terms in the equations that describe interactions between real particles. Their presence, though fleeting, is essential. One of the most striking pieces of evidence for vacuum fluctuations is the Casimir effect. Place two metal plates extremely close together in a vacuum, so close that only certain wavelengths of vacuum fluctuations can exist between them. Outside the plates, all wavelengths are allowed. Inside, the spectrum is squeezed. The imbalance in vacuum energy creates a slight force that pushes the plates together. This force has been measured. It is real. It is the vacuum revealing its restless nature. Another example lies in the Lamb shift, a tiny difference in the energy levels of hydrogen atoms. When theorists tried to predict the electron's energy states using simple models, they were slightly off. Only by including the effects of vacuum fluctuations, virtual particles tugging at the electron's position, nudging it in subtle ways, did the predictions match the observations. The vacuum literally shifts the structure of atoms. Even the magnetic moment of the electron, one of the most precisely measured quantities in all of physics, receives contributions from virtual particles swirling briefly into existence and altering the behavior of the electron's field. These corrections are not optional. Remove them, and the theoretical predictions no longer match reality. The vacuum is not empty, it is active, it is creative. If you drift deeper into the mathematics of quantum field theory, each type of particle corresponds to a field that stretches throughout the universe. Electrons arise from excitations of the electron field. Photons arise from excitations of the electromagnetic field. Quarks arise from excitations of the quark field. The vacuum is what these fields look like when they are not excited by real particles. But even in that quiet state, they cannot lie still. Picture the vacuum as an ocean at night. To your eye, the surface looks calm. But if you watch closely, you see ripples, faint and constant, rising and falling. These ripples are the vacuum fluctuations. They arise not from external disturbances, but from the nature of the ocean itself. If you travel even deeper, to the smallest scales, the Planck length, the vacuum becomes wilder still. Space-time itself begins to flicker. Geometry twists. Tiny wormholes appear and collapse. Virtual black holes form and evaporate. These ideas come from attempts to merge quantum mechanics with general relativity, suggesting that even space and time are not continuous, but granular and restless. The vacuum becomes a storm beneath the smooth surface of reality. But how does this constant creation and annihilation not violate conservation of energy? This is where the uncertainty principle steps in once again. Energy can be borrowed from the vacuum, as long as it is returned quickly enough. The shorter the lifetime of the virtual particle pair, the more energy they can momentarily borrow. This is not cheating. It is a built-in rule of the universe, allowing tiny temporary violations of energy conservation that balance out perfectly over time. The vacuum is like a silent loan office, lending energy in tiny bursts and reclaiming it before anyone notices. But these loans add up. They create measurable phenomena. They influence the behavior of real particles. They shape the cosmos. Some theories suggest vacuum energy might be connected to dark energy, the mysterious force accelerating the universe's expansion. While the connection remains uncertain and the numbers remain challenging, many physicists believe the vacuum's energy plays a role in the universe's fate. If true, the quiet hum beneath reality might be shaping the expansion of space itself. Vacuum fluctuations also affect nuclear decay. In some types of decay, a virtual particle briefly appears and mediates the process. Without these fluctuations, atomic nuclei would be more stable, changing the chemistry of the universe. Even the sun, which relies on quantum tunneling and weak interaction processes, is influenced by virtual particles at every moment. Every beam of sunlight you have ever felt on your skin carries the subtle fingerprints of vacuum activity. As you reflect on all this, a philosophical truth emerges with quiet clarity. Emptiness is not the absence of things, it is the presence of potential. The vacuum is not blank, it is generative. Not in a mystical sense, but in a physical one. It is the foundation upon which reality rests, not as a passive backdrop, but as an active participant. Creation and annihilation happen constantly. Fields pulse, possibilities rise and fall. Even nothing is something. If you float gently back from this shimmering landscape, the next question rises softly, almost inevitably. If the vacuum itself is alive with fluctuations and possibilities, how do particles borrow energy from this restless background? And why does the universe allow these momentary departures from the rules? Let us explore that mystery in the next part. Part 12. How do particles borrow energy from the universe? The energy-time uncertainty principle allows particles to briefly borrow energy as long as they return it within a limit. This borrowing powers vacuum fluctuations, nuclear fusion, and even the stability of atoms. It is not a violation of physics, it is one of its quietest permissions, a temporary bend in the rules that becomes the foundation for many quantum phenomena. If you drift into this idea slowly, you start to feel that the quantum world has its own form of breathing, tiny inhales and exhales of energy, allowed as long as they happen fast enough. Classically, energy is absolute. It is conserved perfectly, without compromise. But in quantum mechanics, the uncertainty principle softens the edges of this rule. It allows the universe a gentle margin of flexibility, not a loophole, not a contradiction, a boundary with softness. According to the energy-time uncertainty relation, the more briefly a process occurs, the less precisely its energy must be defined. For very short-lived events, the energy can fluctuate. These fluctuations are not errors, they are permitted by the mathematical structure of quantum mechanics. For the smallest fractions of time, nature allows a particle or a field to borrow energy from the vacuum. The borrowing is always repaid. The universe keeps perfect accounts. But for that brief moment, possibilities open that classical physics forbids. One of the clearest examples of this borrowing lies in virtual particles. In a vacuum, pairs of particles and antiparticles appear and vanish in tiny intervals of time. Each pair borrows energy from the vacuum to exist, then annihilates to return that energy. They are like sparks rising from embers, present for an instant, then gone, but leaving warmth behind. These virtual particles mediate forces, shift atomic energy levels, and contribute to the interactions that give the universe structure. They are brief, but never meaningless. If you imagine drifting through a vacuum at an unimaginably small scale, you would sense these fluctuations like faint pops of energy, blooming and dissolving in a shimmering background. They are not chaos. They are the natural pulse of quantum fields permitted by uncertainty. The vacuum is not constrained to perfect stillness, it is allowed to whisper. Another beautiful example of energy borrowing is quantum tunneling. When a particle approaches a barrier, it does not have enough classical energy to cross. The uncertainty principle allows the particle's energy to fluctuate just long enough for it to appear on the other side. The particle does not gain permanent energy. It borrows just enough for just long enough to pass through, then returns the surplus within the permitted window. Without this fleeting permission, the sun would never shine. The proton-proton fusion at the core of the sun requires particles to come close enough to overcome their electric repulsion. Classically, they do not have enough energy to do this at the temperatures present, but quantum tunneling, driven by this temporary borrowing, allows them to slip inside one another's reach. Every sunrise you've seen is powered by energy borrowed and returned within the quantum limits of time. A similar phenomenon occurs inside atoms. Electrons occupy discrete energy levels, like steps in a staircase. They cannot sit between levels. But the stability of these levels and the tiny corrections to their energy depend on virtual photons and vacuum fluctuations that arise because the electron's energy cannot be defined with absolute precision at every moment. The small breathing room, permitted by the uncertainty principle, shifts the energies of atomic states just enough to match what we observe. These shifts are not subtle curiosities, they are essential. Without them, atoms would have different spectra. Chemistry would behave differently. The sun's light would carry a different signature. The universe would not be the same. If you drift deeper, you discover that energy borrowing plays a role in the interactions of quarks inside protons and neutrons. In the swirling storm of the strong force, quarks exchange gluons constantly. Gluons spawn virtual quark-antiquark pairs. These interactions rely on energy fluctuations permitted by the uncertainty principle. The mass of the proton, most of the mass of everything you touch, comes not from the quarks themselves, but from the energy of these interactions. Your body, the earth, the stars, everything made of matter is held together by energy that flickers constantly, borrowed and repaid endlessly. If this sounds poetic, it is because nature has built poetry into its mathematics. The universe does not forbid change. It allows brief moments of creative freedom as long as balance is restored. The uncertainty principle is not simply a constraint. It is a negotiation between what must remain conserved and what may fluctuate. Imagine a violin string. When plucked gently, it vibrates in a precise tone, but pluck it harder, faster, shorter. Its pitch becomes uncertain, its harmonics richer. The shorter the vibration, the less precisely its frequency can be defined. The energy-time uncertainty principle behaves similarly. The shorter the event, the broader the range of energies it may briefly explore. These fluctuations add texture to the universe. They make physical laws feel less like rigid gears and more like living systems. The borrowing becomes even more dramatic in the process known as quantum tunneling in nuclear decay. Certain radioactive nuclei emit particles only because the uncertainty principle allows a particle inside the nucleus to briefly borrow the energy needed to escape its confinement. This energy would be forbidden in a purely classical universe, but quantum mechanics gives the particle just enough latitude to break free. Without this borrowing, radioactive decay would be rare. The Earth's interior would not stay warm. Plate tectonics would not operate. Life might never have emerged. Energy borrowing also appears in quantum electrodynamics, the theory describing interactions between light and matter. When an electron emits or absorbs a photon, its energy and position shift according to rules dictated by uncertainty. Temporary energy imbalances are allowed as the particle transitions between states. These transitions give rise to the detailed structure of atomic spectra, those delicate, colorful fingerprints seen in starlight. Every star carries the imprint of quantum borrowing in its spectrum, even in systems far larger than atoms. Energy-time uncertainty plays a quiet role. In superconductors, where electrons pair and move without resistance, the coherence of these pairs depends on fluctuations in the energy of the electron field. In the Josephson effect, electrons tunneling between superconductors generate tiny oscillating currents that arise directly from the interplay between phase and energy uncertainties. These are gentle process, but they reveal something profound. The universe allows temporary imbalances that disappear before they become contradictions. Energetic borrowing is not magic. It is the natural expression of the fact that energy and time are not perfect, independent quantities. Their relationship is fuzzy. The fuzziness allows creation, transition, change. If you reflect on this deeply, you feel a quiet philosophical resonance. The universe maintains order with flexibility, not rigidity. It allows fluctuations, but only within boundaries. It welcomes possibility, but only under guidance. It permits the smallest freedoms in exchange for perfect balance over time. Particles borrow energy the way a tide borrows water from the deep, in cycles, in pulses, in ways that obey the rhythm of the whole. And as you drift from this chapter, another question begins to rise softly from the horizon of thought. If particles borrow energy and return it, and if the vacuum is alive with motion, what does it mean for particles to have no precise position at all? What happens when even location dissolves into probability? Let us continue gently into that mystery. Part 13. Why don't quantum particles have precise locations? Position at the quantum scale is never a single point. Instead, particles are described by probability densities spread across space like soft shadows. Only when measured does the wave function collapse into a definite value. This blur is not a failure of measurement, it is the natural language of the microscopic world, where fuzziness is the rule, not the error. If you drift gently into the quantum world, the first thing you notice is that space itself begins to feel different. In everyday life, we are used to sharp boundaries and clear positions. A cup sits on a table, a stone lies on the ground, a planet orbits the sun along a definite path. Everything has a place. Those places feel permanent. But as you zoom in, past molecules, past atoms, past the cloud of an electron's orbit, certainty dissolves like mist. Quantum particles do not live in the crisp geometry of classical intuition. They live in a landscape of probability. At this scale, a particle is not a tiny bead located at a precise coordinate. It is a wave function, a mathematical description that stretches across space like a faint glow. This glow is not metaphorical. It represents the likelihood of finding the particle at each point in space if you choose to measure it. Before measurement, there is no single point where the particle actually is. The particle's presence is smeared, distributed, blurred. It inhabits many places at once, with different degrees of possibility. This is not because our tools are too crude, it is because nature is too subtle. The Heisenberg uncertainty principle lies at the heart of this phenomenon. It tells us that position and momentum cannot both be known with perfect accuracy. The more precisely you try to determine where a particle is, the less you can know about how it is moving. And if you try to pin down its velocity, the particle's location spreads out. This is not a technological limitation, it is a structural feature of the universe. A particle that has a perfectly defined position would require a wave function infinitely narrow, a spike. But such a wave function contains infinitely many momentum components. The particle would be moving in all directions at once. Likewise, a particle with perfectly defined momentum would have a wave function spread evenly across space. It would be everywhere and nowhere in equal measure. Quantum particles are always a mixture of these extremes. If you visualize the wave function of an electron bound in an atom, it does not look like a tiny marble orbiting the nucleus. It looks like a cloud, soft, shaped, structured. Some regions of the cloud glow brighter, meaning the electron is more likely to be found there. Other regions glow faintly, meaning its presence is possible but less likely. Some regions are dark, nodes where the electron can never be. This cloud is not a guess, it is the electron. The probability distribution is the particle's reality before measurement. When you interact with the electron, when you measure it, the wave function collapses into a single outcome. A position is revealed, a point is recorded. But this moment of certainty is temporary. As soon as the measurement ends, the wave function begins to spread out again, the electron's position dissolving back into probability. This is why physicists say that location is not a fundamental property of quantum particles. It is an emergent one. It arises only through interaction. If you drift deeper into this idea, you encounter the Schrödinger equation, the rule that governs how wave functions evolve. It describes how probability flows, spreads, interferes, and shifts. Under this equation, a localized wave function gradually broadens, like a drop of ink diffusing in water. The smaller the particle's mass, the faster the spread. For electrons, this spread is rapid. For atoms, slower. For macroscopic objects like pebbles or chairs, effectively non-existent. That is why the classical world feels solid while the quantum world feels soft. But softness does not mean vagueness. Quantum mechanics does not say the particle is smeared in an undefined fog. It says the particle's presence is described precisely by the wave function, a function that predicts experimental outcomes with extraordinary accuracy. The fuzziness is not random. It is structured, predictable, beautiful. One of the clearest demonstrations of this behavior comes from electron diffraction. Fire electrons through a crystal and they produce interference patterns, the hallmark of wave behavior. These patterns arise only because electrons, before detection, exist as delocalized waves interacting with the lattice. Their positions are not single points traveling through the crystal. They are extended distributions exploring many paths, interfering with themselves. Another example lies in quantum double well potentials. Imagine a particle trapped between two potential wells, two valleys separated by a hill. Classically, the particle must choose one valley, but quantum mechanically, the wave function extends across both. The particle is not in the left well or the right well. It exists across the entire shape of the potential. It occupies both sides simultaneously, with probabilities defined by the structure of the wells. Only when measured will it decide which well to appear in. If you continue drifting through this landscape, you reach the realm of quantum tunneling. A particle described by a spread-out wave function can sometimes appear on the far side of a barrier. This is not because it burrows through. It is because its wave function never stopped on one side. It extended across the barrier, and the measurement revealed the particle in a place classical physics forbids. In this sense, position is revealed, not possessed. Another profound example arises in quantum field theory. There, particles are not even primary objects. Fields are. A particle is simply a localized excitation, a ripple, in a field that spans the entire universe. The location of the particle is just the region where the field's amplitude is high. As the ripple evolves, it spreads, it moves, it interferes, it dissolves. Position becomes a dynamic feature of the field, not a property of a tiny object. When multiple particles interact, their wave functions combine, they entangle, and the position of one may depend on the position of another. The blur becomes relational. Quantum mechanics suggests that position is not something particles carry individually. It is something that emerges through interaction with the environment. This helps explain why macroscopic objects, like you or the chair you sit on, do not appear fuzzy. They constantly interact with countless particles around them. These interactions collapse their wave functions rapidly and repeatedly, locking their positions into definite values. This process, called decoherence, washes out the quantum blur. The world becomes classical, definite, solid. You're made of particles that have no precise locations, yet you feel grounded, you feel anchored. This anchoring is the result of trillions of tiny measurements happening every moment. If you pause and reflect, a quiet philosophical insight emerges. Location is a conversation between a quantum system and the world around it. Particles do not hold still. They do not sit in one place. They inhabit possibility, not certainty. Position arises through interaction, not essence. And as you drift softly away from this realization, another question begins to form, as gently as a page turning in a silent room. If particles are defined by soft probabilities rather than sharp locations, what determines the shapes of these wave functions? And why do they form the elegant patterns we see in atoms? Let us explore that quiet mystery in the next part. Part 14. Why do identical particles behave as one? Electrons, photons, and other particles of the same type are indistinguishable, not just similar, but fundamentally identical. This perfect identity creates collective behaviors we can't replicate in classical physics. Whether forming the rigid stability of atoms or the flowing coherence of superconductors, identical particles behave in harmony, following shared quantum rules as though they are pieces of one continuous entity. If you drift gently into this idea, the first thing you must release is the classical notion of individuality. In everyday life, two objects may be extremely similar. Two raindrops, two grains of sand, two violin strings, but they are never perfectly identical. Each carries subtle differences. Each has its own microscopic history, its own internal imperfections. But in the quantum world, nature operates differently. Electrons do not have tiny distinguishing marks. Photons do not carry secret labels. Two electrons are not simply hard to tell apart. They are literally indistinguishable in every physical sense. This indistinguishability is not philosophical, it is operational. The laws of physics treat all electrons as the same electron, all photons as the same photon, all protons as the same proton. There is no hidden tag, no encoded identity, no, this one came from that star and that one came from somewhere else. They are identical because their existence arises not from being individual objects, but from being excitations of the same underlying quantum fields. In quantum field theory, there are not many electrons. There is one electron field spread across the universe. Every electron you encounter is simply a ripple in that field, a local excitation of the same underlying entity. From this perspective, identical particles share identity because they are manifestations of the same continuous structure of reality. When you feel this truth, the phrase, "pieces of one continuous entity," becomes literal, not metaphorical. This indistinguishability has profound consequences. The first is the need to treat collections of identical particles not as separate individuals, but as single collective states, wave functions that describe groups rather than individuals. Unlike classical objects, which can be labeled and tracked, identical quantum particles merge into unified patterns of probability that cannot be separated into distinct this one and that one components. Electrons, for example, are fermions, governed by the Pauli exclusion principle. This principle states that no two fermions can occupy the same quantum state. It is a simple rule with enormous consequences. Electrons fill atomic orbitals not by choice, but because quantum identity forces them to avoid each other's states. They arrange themselves into shells. They stack into layers. They occupy different patterns of angular momentum. The entire structure of the periodic table, the diversity of chemistry, the rigidity of solids, the behavior of metals, emerges from this single rule. If electrons were distinguishable, none of this would exist. Atoms could collapse inward, chemistry might not form, the universe would lose structure. The Pauli exclusion principle is the quiet law that prevents matter from falling into itself. Photons, on the other hand, are bosons, particles that follow different rules. Instead of excluding one another, bosons gather happily. They cluster, they accumulate, they share the same quantum state effortlessly. This is why lasers exist. A laser is not a stream of independent photons, it is a coherent collective, photons behaving as one, occupying the same mode, the same frequency, the same direction of travel. The light in a laser is not merely bright, it is unified. Every photon is part of the same quantum identity woven into a single coordinated wave. This difference between fermions and bosons arises directly from indistinguishability. When particles cannot be labeled, their shared identity forces their wave functions to be either symmetric, for bosons, or antisymmetric, for fermions. In symmetric wave functions, swapping two particles makes no difference. In antisymmetric ones, swapping introduces a minus sign, which forces the exclusion principle. These properties are not optional, they are structural. They define the very texture of reality. If you drift deeper, you find even more remarkable phenomena emerging from this shared identity. In certain materials cooled to near absolute zero, enormous numbers of bosons, usually atoms with integer spin, collapse into a single quantum state. This is known as a Bose-Einstein condensate. In such a condensate, millions or billions of atoms behave not as individuals, but as a single coherent quantum wave. Their positions blur together, their momenta align. The entire ensemble acts as one entity, with one identity, one wave function. If you could see it, it would be like watching a cloud transform into a single shimmering droplet of probability, smooth, unified, breath-like in its motion. Another example is superconductivity, where electrons form pairs called Cooper pairs. Although electrons are fermions and normally repel each other, in certain conditions they bind into pairs that behave as bosons. Once paired, they are free from the exclusion principle. They march together through a material without scattering, losing no energy, facing no resistance. Or, current of millions of electrons moves as though it were one long wave sliding effortlessly through the crystal lattice. This collective behavior arises entirely from the particle's shared identity. Quantum indistinguishability also shapes the behavior of neutron stars. When stars collapse under their own weight, electrons are squeezed into protons, forming neutrons. These neutrons, still fermions, stack into dense layers, each layer prevented from collapsing by the exclusion principle. This degeneracy pressure halts the collapse and creates some of the densest objects in the universe. Without indistinguishability, neutron stars could not exist. Entire categories of cosmic objects would vanish. As you drift through these examples, you begin to sense a quiet truth. The individuality we experience at human scales is an illusion created by complexity. Deep down, the universe operates through collective identity, not separation. Identical particles behave as one because they arise from the same underlying field. Their connections are not sentimental or metaphysical, they are structural, embedded in the equations that describe their behavior. This unity shapes everything: the stability of atoms, the behavior of light, the emergence of superconductivity, the glowing precision of lasers, the quiet strength of neutron stars. The universe does not build matter out of isolated building blocks. It builds matter out of rules that apply to patterns, patterns woven through identical entities that behave not like individuals, but like chapters of the same story. This collective identity extends even to statistical mechanics. Fermions obey Fermi-Dirac statistics. Bosons obey Bose-Einstein statistics. These statistical rules define how particles fill energy levels, how they distribute themselves, how they share or avoid specific states. You cannot describe a gas of electrons the way you describe a gas of classical particles. Quantum identity changes everything, even how particles count. If you reflect on all this, a soft philosophical insight emerges. The universe's smallest components gain meaning not through difference, but through sameness. The harmony of electrons in atoms, the coherence of photons in lasers, the unity of atoms in condensates, all arise from particles acting collectively, as if each one is a note in a single continuous chord. And as you rise gently from this chapter, letting these patterns settle like dust in the quiet of your mind, another question surfaces softly, almost inevitably. If identical particles behave as one, what happens when we consider the universe as a whole? What large-scale patterns emerge from the shared rules of the quantum world? Let us continue into that mystery next. Part 15. Why does quantum mechanics feel so philosophically strange? Everything about quantum mechanics challenges human intuition. We evolved to sense weight, distance, and motion, not probability fields, superpositions, or non-local connections. The quantum realm reminds us that reality is larger, stranger, and more intricate than our instincts suggest. It is a domain where nature expresses itself in whispers rather than certainties, inviting us to listen with patient curiosity rather than expectation. If you move gently into this final chapter of the quantum landscape, the strangeness arrives not as shock but as softness. It is not loud or confrontational. It is quiet, like a distant hum. A subtle shift in perspective that begins the moment you release the idea that reality must conform to human intuition. Our senses evolved in a world of large objects, trees, stones, rivers, bodies. Our intuition was shaped by survival in a mid-sized universe where motion is classical, distances are local, and outcomes feel certain. But the quantum world is not mid-sized. It is not classical. Its rhythms and rules were never meant to align with the habits of creatures navigating a world of everyday scales. So when we enter its territory, we feel as though we are stepping into a dimension where our familiar concepts have been stretched into unfamiliar shapes. Quantum mechanics is philosophically strange because it reveals that we are not prepared, biologically or intuitively, to understand the deepest structure of the universe without letting go of the stories our senses tell. One of the first philosophical shocks comes from superposition. In our everyday world, something is either here or there. A door is either open or closed. A light is either on or off. Yet at the quantum level, particles occupy many states at once. This is not abstract, and it is not metaphor. It is measured, it is observed, it is repeatable. But to our classical minds, it feels like a violation of logic. It demands a new kind of intuition, one that accepts that existence itself can be diffuse, layered, unresolved until observed. Superposition teaches that reality can hold many possibilities without choosing, and that the act of choosing is not built into the fabric of the world, but arises through interaction. This alone is philosophically profound. Equally strange is the idea that the observer matters, not because consciousness has special power, but because measurement is interaction. When a quantum system interacts with the environment, light bouncing off it, a detector responding to it, another particle colliding with it, the wave function collapses. Possibilities narrow, outcomes sharpen, reality crystallizes into a single form. To us, this feels personal. It feels as though the universe cares whether we are watching. But the deeper truth is more subtle. The universe transitions from probability to outcome whenever information is exchanged. Observation feels fundamental not because we are special, but because interaction is fundamental. Quantum mechanics is also philosophically strange because it challenges determinism. Classical physics gives us a world where, if we know the initial conditions perfectly, the future follows inevitably. But the quantum world replaces inevitability with probability. Even if we know everything about a system's wave function, the result of a specific measurement can only be predicted with likelihoods. Reality becomes a story of weighted outcomes, not fixed certainties. This does not mean the universe is chaotic. Quantum mechanics is extremely precise and deeply structured, but its structure is probabilistic. It invites us to accept that unpredictability is woven into reality at the smallest scales, not as error, but as essence. Then comes entanglement, perhaps the most philosophically disruptive idea of all. Two particles become linked in such a way that their states correlate instantaneously, no matter how far apart they travel. To classical minds, this feels like communication. But it is not communication, it is correlation, perfect, instant, and baked into the joint wave function that spans both particles. When one particle's state is measured, the other's state becomes known, not because something travels between them, but because the two were never separate in the first place. Quantum mechanics forces us to rethink the word separate. It reminds us that distance is not as fundamental as relationship. That locality does not define reality the way we once believed. Entanglement tells us that information can be shared across space, not by sending signals, but by sharing identity. Then, there is the philosophical weight of uncertainty. In the quantum world, we cannot know everything at once. Position and momentum resist simultaneous precision. Energy and time blur into one another. Effortlessly, the universe sets soft boundaries on knowledge, not because it is hiding something, but because certain combinations of properties are not simultaneously meaningful. This is not a failure of inquiry. It is a feature of nature. If you reflect on uncertainty long enough, you realize that it has emotional implications as well. It reminds us that knowledge is always partial, that clarity often comes with trade-offs, that every measurement, every question we ask of the universe shapes the answer we receive. Philosophy has debated this idea for centuries. Quantum mechanics embeds it in physics itself. Then there's the strangeness of fields, which reveals that particles are not fundamental objects, but excitations, ripples of underlying fields that fill the cosmos. Electrons, photons, quarks, gluons. None of them are standalone ingredients. They are patterns in something deeper. When the ripple moves, we call it a particle. When the ripple is still, we call it the vacuum. This is profoundly unintuitive for creatures built from atoms and molecules that seem solid. Quantum mechanics does not describe a universe made of little bits. It describes a universe of continuous underlying fabric from which bits emerge. The philosophical tension grows when we realize that our macroscopic world is classical only because decoherence hides the quantum behavior beneath it. The particles in your hand are quantum. The atoms in your bones are quantum. The electrons filling your nerves are quantum. But because these systems interact with the environment endlessly, light striking them, air molecules bouncing off them, thermal energy vibrating them, their wave functions are constantly collapsing. They cannot maintain delicate superpositions. They appear solid, definite, familiar. Quantum strangeness is not absent from our world. It is simply washed out by noise and interaction, like delicate ripples erased by a churning sea. The philosophical weight of all this becomes clearer when you ask a simple question. What, then, is reality? Is reality the set of outcomes we measure? Is it the wave function that encodes all possibilities? Is it the underlying field that carries these possibilities? Is it something else entirely? Different interpretations of quantum mechanics answer differently. The Copenhagen interpretation emphasizes collapse. The many worlds interpretation removes collapse entirely. Pilot wave theories reintroduce deterministic trajectories guided by a wave. Cubism emphasizes the role of information and beliefs. Decoherence theories focus on environmental entanglement. Quantum mechanics does not tell us which of these interpretations is right. It only tells us which predictions match experiments. This is philosophically uncomfortable because we crave neat explanations. But the quantum world resists neatness. It is richer, softer, more intricate. It tells us gently that our craving for certainty is rooted in a scale of existence that is not fundamental. Quantum mechanics is not strange because it is illogical. It is strange because it is more logical than we are capable of intuitively grasping. It lives in a mathematical terrain deeper than instinct. If you sit with this long enough, the strangeness begins to feel less like contradiction and more like invitation. An invitation to widen your intuition, to accept that the universe does not owe us familiarity, to appreciate that reality is not obligated to feel natural at human scales. Quantum mechanics feels philosophical because it forces us to look beyond ourselves. And as we drift toward the close of this journey, one final truth emerges quietly, like a whisper rising through still air. The quantum realm is not trying to confuse us. It is simply showing us that the universe is larger, gentler, and more mysterious than the stories evolution wrote into our minds. And in that gentle mystery, there is room for wonder. There is room for humility. There is room for awe. When you are ready, we can move into the outro.